PM and PSK. In the world of communication, phase modulation, PM, and phase shift keying, PSK, are two sides of the same coin. They both transmit information by changing the timing or phase of a radio wave, but they differ in how they handle that information. What is phase modulation, PM? Phase modulation is an analog modulation technique. It encodes a continuous message, like a human voice, by varying the instantaneous phase of a carrier wave in direct proportion to the amplitude of the message signal. How it works: if your voice signal goes up, the phase of the carrier wave shifts forward. If it goes down, the phase shifts backward. The math: a PM signal is generally represented as carrier amplitude, carrier frequency, phase sensitivity, the message signal, data, key characteristics, constant amplitude. The signal strength doesn't change, making it very resistant to noise, which usually affects amplitude. Relationship with FM, PM is mathematically related to frequency modulation, FM. In fact, changing the phase rapidly also changes the frequency, which is why they are both called angle modulation. What is phase shift keying, PSK? Phase shift keying is the digital version of phase modulation. Instead of a continuous wave of information, it uses discrete, sudden shifts in phase to represent binary data, zeros and ones. 11 Common types of PSK, BPSK, binary PSK. The simplest form 12. It uses two phases, usually and. One phase represents 0 and the other represents 1. QPSK, quadrature PSK. It uses 4 phases, example. Since there are 4 options, each shift can represent 2 bits at once, 0 0, 0 1, 10, 11, doubling the data rate. 18 PSK/16 PSK. These use even more phases to pack more bits into every shift, though they become more sensitive to interference as the phases get closer together. Comparison at a glance. Feature: phase modulation, PM, phase shift keying, PSK, signal type analog, continuous, digital, discrete, usage: sound synthesizers, older radio, Wi-Fi, Bluetooth, satellite TV. Representation: proportional wave shifts, constellation points, dots on a map. Complexity: simple concept, hard to demodulate, requires precise synchronization. Why does this matter? Most modern technology uses PSK because computers think in digital bits. When you use Wi-Fi or Bluetooth, your device is essentially keying the phase of a high-frequency wave thousands of times per second to send your data. CPM and CPSK. Building on the concepts of PM and PSK, continuous phase modulation, CPM, and continuous phase shift keying, CPSK, address one of the biggest challenges in wireless communication: the jumps in a signal. 1. What is CPM, continuous phase modulation? In standard digital modulation, the signal phase can jump instantly, example from 2. These sharp transitions create spectral splatter, where the signal leaks into neighboring frequencies. CPM is a family of modulation techniques designed to avoid this by ensuring the phase changes gradually and smoothly over time. The phase memory: in CPM, the phase of the current symbol depends on the previous symbols. It's like a car turning a corner. It doesn't instantly snap to a new direction, it follows a smooth arc constant envelope. Because the phase is continuous, the amplitude of the signal remains perfectly constant. This allows engineers to use high-efficiency nonlinear amplifiers, like Class C, without distorting the signal, which is critical for saving battery life in mobile devices. 2. What is CPSK, continuous phase shift keying? CPSK is effectively a specific implementation of CPM. In technical literature, it is often used interchangeably with CPFSK, continuous phase frequency shift keying. While standard PSK, like QPSK, has those abrupt keying shifts, CPSK uses a frequency shift to transition between phase states. Because frequency is the derivative of phase, a steady frequency shift results in a smooth, linear change in phase. Key example: minimum shift keying, MSK. The most famous version of CPSK is MSK. It is considered the cleanest way to send digital data because, 1. The phase shift is exactly per bit. 2. The frequency spacing is the minimum possible that still allows the receiver to distinguish between a 0 and a 1. 3. Why do we use them? If you look at the sidebands, the noise around the main signal, CPM and CPSK, are much quieter than standard PSK. Narrow bandwidth: because there are no sharp jumps, the signal fits into a much smaller slice of the radio spectrum. Power efficiency: you get more range out of your battery because the constant envelope signal doesn't require expensive, power-hungry linear amplifiers. Real-world use: GMSK, Gaussian minimum shift keying, a type of CPM, was the backbone of GSM, 2G, cellular networks and is still used in technologies like Bluetooth and ACE, marine tracking. 4. Comparison summary. Feature: PSK, digital PM, CPM/CPSK. Phase change: abrupt/instant, smooth/continuous, spectral width wide, requires filtering, very narrow, cleaner, envelope fluctuates constant, high efficiency, complexity simple receiver complex receiver, needs viterbi/trellis. FM frequency modulation, FM, is an analog modulation technique where the frequency of a carrier wave is varied in direct proportion to the amplitude of the message signal, like music or voice, while the amplitude of the wave remains constant. If you think of a radio wave as a vibrating string, FM doesn't make the vibrations taller, that would be AM, it makes them faster or slower depending on the information being sent. How FM works in FM, the information is hidden in the crowding and spacing of the waves. High amplitude message, when your voice gets loud, the carrier wave frequency increases, the waves get closer together. Low amplitude message, when your voice gets quiet, the carrier wave frequency decreases, the waves spread out. Zero amplitude, the carrier stays at its resting or center frequency. The mathematical formula the FM signal is represented as, amplitude of the carrier, remains constant. Center frequency of the carrier. Frequency sensitivity, how much the frequency shifts per volt of input. The message signal being sent. 2 FM versus AM, why FM sounds better. The main reason we use FM for high fidelity music is its noise immunity. Resistance to static, most natural interference, like lightning or engine noise, affects the amplitude of a radio wave. Since an FM receiver only cares about the frequency, the timing of the peaks, it can use a limiter to clip off any noisy amplitude spikes without losing any actual data. Capture effect, if 2 FM stations are on the same frequency, the receiver will lock onto the stronger one and completely ignore the weaker one, rather than playing both at once, which happens in AM. Higher bandwidth, FM uses a much wider range of frequencies per station, typically 200 kHz, compared to AM, 10 kHz. This allows it to carry a much richer range of audio frequencies, including stereo sound. 3 key concepts in FM frequency deviation: the maximum distance the frequency moves away from the center point 14 for standard FM radio, this is usually kilohertz. Modulation index, $/beta, the ratio of the frequency deviation to the frequency of the message. It determines how many sideband the signal has. Carson's rule, a rule of thumb used to estimate the bandwidth required for an FM signal. 15.4. Real-world applications: FM broadcasting, high-quality music radio, 88.0 MHz to 108.0 MHz. Two-way radios, used by police, fire departments, and walkie-talkies, usually narrowband FM to save space. Television, in old analog TV, the video was sent via AM, but the audio was sent via FM telemetry, sending data from sensors in satellites or weather balloons. Demodulation of FM signals. Demodulation is the process of extracting the original message, like audio, from a frequency-modulated wave. Since the information in FM is hidden in the timing, frequency, rather than the strength, amplitude, the goal of a demodulator is to act as a frequency-to-voltage converter. Here is an introduction to how this is achieved, ranging from simple analog methods to modern digital techniques. 1. The core requirement: frequency-to-voltage conversion. An FM demodulator must produce an output voltage that changes in sync with the input frequency. To do this effectively, the circuit must follow 3 rules. 1. Linearity, the voltage change must perfectly match the frequency shift to avoid distortion. 2. Noise rejection, it should ignore changes in amplitude, static/noise. 3. Sensitivity, it must detect even tiny shifts in frequency. 2 Common analog demodulators. Before digital chips, radios used clever analog circuits to translate frequency into sound. A. The slope detector, simple but flawed, this is the most basic method. It uses a tank circuit, inductor and capacitor, tuned slightly away from the carrier frequency. How it works: as the FM signal's frequency shifts, it moves up or down the slope of the circuit's resonance curve. This causes the output amplitude to change. Result: it turns FM into AM, which is then decoded with a simple diode. Drawback: it is very sensitive to noise and has poor linearity. B. Foster-Seeley discriminator, a more advanced version that uses a specialized transformer to compare the phase of the primary and secondary windings. It provides much better linearity than a slope detector but still requires a limiter circuit to strip away amplitude noise before processing. C. The ratio detector. This was the standard in older FM radios. It is similar to the Foster-Seeley but includes a large capacitor that stabilizes the voltage. This makes the circuit naturally immune to amplitude noise, meaning a separate limiter stage isn't strictly necessary. 3. Modern demodulation, the phase-locked loop, PLL, in modern electronics and ICS, the PLL is the gold standard for FM demodulation. It doesn't rely on slopes or tuned transformers, instead, it uses a feedback loop. 1. Tracking, the PLL contains a local oscillator, VCO, that tries to lock onto and track the incoming FM frequency. 2. The error signal, to keep the VCO perfectly matched to the incoming signal, the PLL generates a correction voltage. 3. The output, because the correction voltage has to follow the frequency changes of the input signal exactly, that voltage is the original audio signal. For digital demodulation, SDR, in software-defined radios, SDR, demodulation is done with math. The computer takes the complex signal, I and Q components, and calculates the instantaneous phase. By taking the derivative, rate of change, of the phase over time, the computer determines the instantaneous frequency. Subtracting the carrier frequency leaves only the original message. Comparison summary method: complexity, quality, noise, immunity, usage, slope detector, very low, poor, non-basic, DIY kits, ratio detector, medium, good, built-in, vintage radios, PLL, high, internal, excellent, high, modern, ICS/receivers, digital, I/Q, software-based, perfect, high, smartphone/SDR.